Okay, do you have any questions? Any questions about the solutions of the midterms also? Did you have a chance to go through the solutions? Any other questions about any of the things that we have been covering? Okay, so let's continue our discussion of the harmonic oscillator. It's kind of our toy model, but at the same time, it's one of the most relevant questions in physics that in most problems, in most research, basically you are making an approximation to the harmonic oscillator. So we had already calculated, for example, the time dependence of the operators, the P and the T, the P and the momentum and the coordinate operator. But now let's do something slightly different. So we know that any operator in the Heisenberg picture, the time dependence would be given by e to the power what's the time dependence? What are the powers of the first exponential? Minus I over h bar ht. And the second one will be I over h bar ht. Well, quite often we will have such expressions. So where we have an operator on one side we have a unitary operator, or on the other side we have the inverse of that operator, let's say, not necessarily unitary. Now we have a general identity relating these expressions. Let's say, suppose we have any operator, not necessarily Hamiltonian, but e to the power I, let's say minus I, some parameter lambda times b, the operator b multiplying a e to the power I lambda b. Now let us call this f of lambda for arbitrary operators a and b. We can obtain an expansion of this one. Basically, these exponentials of operators we always interpret in terms of their Taylor expansions. So if you just Taylor expand the exponentials, you will always get and then make this product, you will end up having a Taylor expansion in lambda. So this f of lambda will be some f0 plus f1 of lambda plus f2 of lambda, lambda squared, plus etc. Now the question is, what are these f0, f1, and f2s? Well, the general theory on Taylor expansion tells me that fn, well, let me also put the 2 factorial over here, 1 factorial over 0 factorial, etc. And these fn's are nothing but the derivative of f lambda with respect to lambda, the nth derivative, evaluated at lambda is equal to 0. So let's try to see if there's some kind of a general pattern in these derivatives. Now, f of 0, what is f of 0? It's just a. So I just put, there are no derivatives, the number of derivatives is 0. You just put lambda is equal to 0, you end up having a. Derivative of f with respect to lambda. Well, the derivative of the first term is minus I b e to the power minus I lambda b, a e to the power I lambda b, plus the derivative of the second term, e to the power minus I lambda b, a e to the power I lambda b times ib. And now if you set lambda is equal to 0, df over d lambda, evaluated at lambda is equal to 0. This is just minus I ba minus ab minus I, the commutator of b and a. Now let me rewrite this df over df by d lambda in a slightly different form. This is minus I e to the power minus I lambda b, the commutator of b and a, e to the power I lambda b. So basically taking the derivative of this f with respect to lambda replaces a with whatever is in between those exponentials with its commutator with b and a with an additional factor of I, a minus I. Well, if you take a second derivative, well, the derivative with respect to lambda always will replace the operator in between these exponential by its commutator with b with a factor of minus I. So the second derivative will also do the same thing. So there will be an additional factor of minus I, and the operator in between will be replaced by its commutator with b. Well, you can basically generalize it to the nth derivative. Each derivative brings a factor of minus I, so we have n of them. And again, each derivative just embeds this commutator with a commutator with b. So we will have e to power minus I lambda b, 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 a, e to power I lambda b. And here there are n b's. So we have basically the general formula that e to power minus I lambda b times a e to power I lambda b. This is equal to a plus minus I commutator of b and a times lambda plus minus I squared, the commutator of the commutator, lambda squared over 2, and so forth, over 2 factorial, and minus I to the power n b, 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 a times lambda to the n over n factorial. Plus, of course, we have all the other terms. So this is called the Baker-Hausdorff formula for these such terms. Now we can apply it to our time evolution. So shall we look at the time evolution of A dagger, or X and P? Which one would you prefer? Some sound? A. So the time evolution will be given by A of t will be equal to e to power minus I lambda b. Now lambda is t over h bar times h times a e to power I over h bar th. Of course, we need these commutators. So the commutator of h and a is equal to a minus h bar omega. So does a lower the energy or increase the energy? It lowers. So that's why it's minus. So you can just test it like this. HA minus AH acting on some state, let's say E alpha, will be equal to H, A acting on E alpha, minus E alpha times A E alpha. Well, this is E alpha minus h bar omega. This has an energy E alpha minus h bar omega minus E alpha A E alpha. So E alphas will cancel. So we end up having minus h bar omega A. Now, if you cannot remember whether it was the H commutator with A or A commutator with H, or whether it is minus h bar omega or plus h bar omega, just you can derive them using what you know, that the A lowers the energy. So it should be a minus h bar omega. Now this is kind of interesting because the commutator of A with H is proportional to A. Well, we have n commutators we have the commutators of commutators and commutators of A. Well, each commutator will bring a factor of minus h bar omega and A. So if you just have H, commutator H, commutator HA, let's say you have n times, each commutator will bring minus h bar omega, A will remain. So this is the general commutator. So A of t, guys, we could just look at the derivative of A of t if you wanted. But this is just an alternative means of evaluating the same thing. So in this case, this is harder than taking the derivative of A, but for some other cases, this method will be just a bit more clear. Now, A of t will be equal to minus, so it has minus I t over h bar to the power n for the general term. Remember, look at it. If you remember our Baker-Hausdorff formula, each term has a minus I lambda times lambda to some power. The nth term has n of them. And plus each term has minus h bar omega to the n because of those n commutators times A summed over n from 0 up to infinity. So this is equal to, from n 0 to infinity, I omega t to the power n, so there's also this 1 over n factorial multiplying A. So now we have what A of t is. So what is that sum? This one. Okay. You see, here we have many terms. Okay. The nth term has n recursive commutation relations. Okay. If you look at the nth term, first of all, it has a minus I lambda over to the power n over n factorial. Now, in our case, lambda is nothing but t over h bar. So this is minus I t over h bar to the n. This is minus I times lambda to the power n divided by n factorial. Now, each commutator brings a factor minus h bar omega. Each recursive commutator. The nth term has n of them. So I have minus h bar omega to the power n. The commutator of A with H is always proportional to A. So if we have n recursive commutation relations, all of them will be proportional to A with each commutator bringing minus h bar omega. So that's why I have this A over there. But A doesn't depend on n, so I can basically take it out of the commutation, out of the summation sign. All the terms are proportional to A. What is this sum? This is the exponential of I omega t over, I omega t times A. A, let's say, at t equal to 0. Now we can either do the same thing for a dagger or just take the dagger of this one a dagger of t is exponential of minus I omega t, a dagger of 0. Now, what about x? Well, I would just ignore the proportionality constants. You can just look them up. X was, if you remember, it was proportional to a plus a dagger. With some proportionality constant. And because basically a was nothing but with a proportionality constant x minus I, another proportionality constant p, and a dagger x plus I, the same proportionality constants. So if I just sum them up, I obtain x. So let me call this coefficient C1, this one C2. So this is equal to, with some proportionality, e to power I omega t, C1 x0 minus I C2 P0 plus e to power minus I omega t C1 x0 plus I C2 P0. And this is equal to some proportionality constant x0 times C1 times twice cosine omega t plus minus C2 times P0 times twice sine omega t. Well, if you put in the proportionality constants and C1 and C2, you will see that this is exactly the result that we had derived before.
Hocam şurada x0 dagger olması gerekmiyor mu?
Correct. That is x0 dagger. What is x0 dagger? x0, x is a Hermitian operator. Similarly, P0, in the second line, P0 should be P0 dagger, but since P0 is a Hermitian operator, its dagger is equal to itself. Now, any questions? Because I will basically close this subject of the operator method in harmonic oscillator, and we will start studying the Schrödinger equation.
Expectation value'larında nasıl bir değişiklik olur?
With time. Well, just take the expectation value of this. You see the expectation value, just multiply, sandwich it between a bra and the ket. But they see 1, 2, or cosines and sines, they are just numbers which you can just take out of that, out of the inner product, bra and ket. So what remains inside between the bra and the kets are the operators, which is x of 0 and p of 0. And this relation will hold whatever your state is. Well, we had already written down an equation for the time dependence of our state kets. So we had, if you remember, we had the alpha t0, this was our state at the time t0, and at the time t it was given by this time evolution operator multiplied being my initial state. Then we looked at the derivative of this state with respect to time. This was equal to the derivative of u with respect to time, alpha t0. But that derivative, when we were studying the time evolution operator, we had also shown that that derivative was nothing but, what is that derivative? Minus I over h bar, h times u. And this basically tells me that the time derivative, let's say minus h bar, the h bar over I, times the time derivative of my ket at the time t, this was given by h acting on alpha t0 at the time t. So this was the Schrödinger equation in a sense, acting in terms of my kets, time-dependent kets. Now this is not the so familiar form of the Schrödinger equation. We usually write it in position space. So what we do is we basically take the time the time derivative of the ket is again a ket. So the wave function we had defined as the expansion coefficients in a basis in which the position operator was diagonal. So basically the time-dependent Schrödinger equation we would obtain from this equation. Now let me put x only, minus I or minus I h bar d by dt alpha t0 t. This is equal to h. Well, for the Hamiltonian, I will assume that it has such a form. P squared over 2m plus v of x. Now the left-hand side, since the position eigenket x doesn't depend on time, I can just take that time derivative out of my inner product. So the left-hand side just becomes I h bar del by del t of x alpha t0 t. Well, it becomes the partial derivative because that inner product depends on the position and also time. But I'm only taking the derivative with respect to time. So that's why I converted it to a partial derivative with respect to time. This should be equal to, well, we had already studied what the momentum operator does in position space. It's just a derivative. We have two of them, so it's the second derivative. So it's minus h bar squared over 2m, the Laplacian, acting on this inner product. The x inside v, inside the potential, is an operator. And the x in my bra is a number. So if you want to make the distinction more explicit, let me put a hat over there, meaning that that is an operator inside my potential. But that operator acting on the ket x, x hat, acting on x is just x multiplying the ket, because those kets are eigenkets of the position operator. And that basically tells me that that term just becomes this term. Now in that second line, x is just a number, it's no longer an operator. It already that position operator acted on the bra x, so the operator just became its eigenvalue in a sense. And if we just denote this inner product, as my wave function. Let me use the three-dimensional notation from now on. So we have this this Schrödinger equation. So it also depends on time t. This is equal to minus h bar squared over 2m Laplacian plus v of x multiplying psi of r t. Now let me also change this to r. And this is my time-dependent Schrödinger equation. This one. No, this is not the harmonic oscillator. V can be any potential. We don't know the Hamiltonian in the quantum mechanical system. But what we do know is if a system has a classical limit, the Hamiltonian we use should reproduce the classical results. In particular, the equation of motion. It should reproduce the same equation of motion in the Heisenberg picture, at least. So that the classical results will be incorporated into the quantum mechanical description. So at least for systems that have a classical limit, this is probably the best choice of the Hamiltonian. It's probably not the only choice. You can make alternative choices, but at least this choice already incorporates the classical results. Now, for systems that don't have a classical limit, what will be the Hamiltonian? Now, that is called research. So that's a research problem. For example, if you have fermions, classically we don't have an analog of fermions, so we don't really know what the Hamiltonian of the fermions should be. But then it was the Dirac who came up with its Dirac equation, and from where we can derive the Hamiltonian of the fermions, and it works. That's what we know.
Hocam, analitik mekanikte Hamiltonian her zaman toplam enerji eşit olmuyordu. Eğer öyle bir sistemin olursa burada yine Hamiltonian yerine doğrudan kinetikle potansiyelin toplamını yazabilir miyiz?
Well, you see, if your Hamiltonian is written in terms of the kinetic plus the potential energy, then the energy is the Hamiltonian. There is no explicit time dependence, so Hamiltonian and the energy are the same. Now, for more complicated systems, for example, if you, let's say, instead of using Cartesian coordinates, let's suppose you use spherical coordinates. You just go to other generalized coordinates. And you just, here what we had done was we basically said that the quantum commutation relations of the position and momentum are equal to the classical Poisson brackets up to a constant, up to a proportionality constant of IH bar. It works only in Cartesian coordinates. If you go to spherical coordinates, it doesn't work. So basically the switch from classical to quantum physics is not as straightforward as it seems here. So if you just want to use the explicit form of the Hamiltonian, you should stick with the Cartesian coordinates, one thing. Second thing, if you have time dependence, well, that's already a problem in quantum mechanics. So if it's time dependent, what do we mean by time energy eigenstates? Hamiltonian changes with time. So you don't get the time-independent Schrödinger equation, etc. But fortunately, at least at the fundamental level, at the subatomic level, all the potentials, all the forces we have, there's no time dependence. So it's enough for us to restrict ourselves to time-independent Hamiltonians with Cartesian coordinates. Also, for example, if you have dissipative systems, what do? You don't have Hamiltonian formalism for dissipative systems. So if you want to Well, the question whether a Hamiltonian description exists, a quantum mechanical description exists, is by itself a problem. Well, we should somehow be able to describe them, but the Hamiltonian, what the Hamiltonian is. But again, we will restrict ourselves to the cases where this similarity between the classical and the quantum pictures are kind of straightforward. Now let's look at what happens when we have here we had started looking at an arbitrary ket. Now let's see what happens if this ket was a stationary state to start with. Alpha T0 is a stationary state. If alpha T0 is a stationary state. Then we know what alpha T0 at the time t is. This is nothing but e to power minus I over h bar e alpha t minus T0 alpha T0. So its time derivative is just minus I over h bar e alpha times itself. And if you just look at the equation in our first line, put this over there, we see that E alpha T0t, this is equal to H acting on alpha T0t. It stays as an energy eigenstate with the same energy. This is, of course, assuming Hamiltonian is time independent. Otherwise, we cannot do this. Now, if this is the case, you can just multiply it with the bra x. Just repeat the previous derivation, and we would end up having E alpha psi alpha of r at the time. Well, there is no time dependence here. This is equal to minus h bar squared over 2m Laplacian plus v of r acting on psi alpha of r. Where now psi alpha of r, we define it as the wave function corresponding to this state alpha. And this is called the time-independent Schrödinger equations. Now let's write it in a slightly different form. Now the Laplacian acting on psi alpha is equal to 2m over h bar v of r minus e alpha psi alpha. And in fact, in one dimension, let's look at the one-dimensional case for simplicity. This is just the second derivative of psi with respect to x squared. This is equal to 2m over h bar v of x minus e psi. Well, we can consider the behavior of this function in different regions of space. So, for example, let's assume that we are looking at a point. If Vx is, let's say, larger than E at a certain region of space. Well, that means the second derivative is always positive. Well, the second derivative is always positive, means the first derivative is always increasing. Well, the first derivative is the slope. So the slope of this function is always increasing. So how will it look like as a function of x? It can have this behavior, or it can have this behavior. Again, the slope was, at least in the, let's say this is the 1, this is the 2. If it behaves like 2, the slope was negative to start with, and it is approaching 0. In the case of 1, it was positive to start with, and it is increasing. Well, of course, it can just go down and go up. That's also another possibility. But these are the only possibilities in this region. If Vx is less than E, hold on, sorry. Just one mistake. Let's say this is psi, this is x. And we are looking in a region where Vx is larger than 0. Larger than E. So Vx minus E is positive. It might be that psi is positive. Then the second derivative is positive. If the second derivative is always positive, that means it's either behaving like this or like this in that region. Now, the other possibility is psi is negative in this region. If psi is negative in that region, then Vx minus E is positive, so the second derivative is negative, second derivative of my function. If the second derivative of my function is negative, that means the slope is always getting smaller and smaller. So in that case, it will behave either like this or like this. These are the possible behaviors we have. Now let's look at the other case. If Vx is less than E, so the basic thing over here is that the wave function is kind of trying to avoid the psi is equal to 0 in those cases, if Vx is larger than E. It will try to avoid it as much as possible. Now let's look at the other case. If Vx is less than E. Now if Vx is less than E, then this parenthesis is negative. So let's again try to plot it, psi as a function of x. Now if psi is positive, the second derivative is negative. So if psi is positive, second derivative negative just means it will have such a behavior. If psi is negative and the second derivative is, if psi is negative, the second derivative will be positive, it means it has such a behavior. Basically, if Vx is less than E, or the energy is larger than the potential energy in a given region, the wave function will try to go to psi is equal to 0 point. Well, let's say if you follow this trajectory, it tries to go to the psi is equal to 0 point. It can cross it. It moves the other side. Now it will again try to go back to the psi is equal to 0 line. So it will be oscillating. So we have oscillatory solutions. Now, this is what's called the classically allowed range. So classically, the particle can only be in regions where its energy is larger than the potential energy. But in the classically forbidden region, where the energy of the particle is less than the potential energy of the particle, the wave function still can be non-zero, but it will be exponential. There won't be any oscillations in that case. There are no oscillations. This basically allows you to kind of sketch what the wave functions should look like. You see, just as an exercise. Let's look at the simple harmonic oscillator. The wave function, well, you see, I'm looking at whether the second derivative is positive or negative. Well, the second derivative is proportional to the difference of the potential and energy multiplied by the wave function itself. So to determine the sign of the second derivative, of course I'm making the assumption that the wave function is real, in this case at least. To determine the sign, I have to, the sign of the second derivative, I have to know the sign of the wave function itself. So it's not enough to know that V is larger than E or less than E. So if V is larger than E, the second derivative will be positive if psi is positive. If the wave function is positive, then the second derivative is positive. If the wave function is negative, then the second derivative is negative. I just looked at first the case when the wave function is positive. That is, the second derivative is positive. That means the slope is constantly increasing. Well, you can have basically those two shapes. This is when psi is larger than 0. When psi is less than 0, the second derivative is negative. That means the slope is constantly decreasing. If you start with a positive slope, it will decrease, it will become horizontal, more and more horizontal. If you have a negative slope, well, it will become steeper and steeper. So those are the two possible behavior you can have if psi is less than 0. Of course, you can start from a positive slope, slope becomes 0, and then it becomes a negative slope and it goes to minus infinity. That's also a possibility. But the idea is, whatever the behavior is, it's trying to avoid the psi is equal to 0 line. If it's initially going towards the psi is equal to 0 line, it will try to avoid it, whether from positive side or negative side. If it's already going away from the psi is equal to 0 line, it will go away faster. So there's no oscillation over there. In this case, in the second case, where in the classically allowed region, the behavior is always trying to go to the psi is equal to 0 line. So it just makes oscillation. So here is the psi is equal to 0 line. It tries to go there. It will overshoot. But then it will again try to go to the psi is equal to 0 line and so on. So it will have this oscillatory behavior. Now, let's say this is x. This is the potential. V of x is equal to 1 over 2 m omega squared x squared. Well, the potential has such a shape. It's a parabola. Let's say if the energy of the oscillator is somewhere over here, well, in this region it will be oscillating. No, sorry. When it reaches the, let's say, the potential barrier, it will just exponentially decay. Well, it cannot increase because in that case, if it starts increasing, its integral will not be finite, so we cannot normalize. And on the other side, again, here we have this exponential tail. So this will be the general behavior of the wave functions in the simple harmonic oscillator. And in fact, these are what we call the nodes number of times it crosses the psi is equal to 0 line, the number of nodes is equal to the excitation level. So the ground state doesn't have any nodes. Basically, it cannot oscillate. It has this somewhat Gaussian-like shape. The first excited state has a single node. The second excited state has 2 nodes. The third excited 3 nodes, etc. So if this is the ground state, the wave function has such a shape. The first excited state will basically have such a shape. Oh, sorry. So it's trying to, the first excited state is first trying to go, if you start from the origin, it tries to go to the 0 line, but the classically forbidden region is very close. It cannot reach the 0 line. It basically just, after it reaches the classically forbidden region, it tries to avoid the 0 line, so it just exponentially goes to 0. In the first excited state, well, it starts from, in the origin it starts from 0. It's increasing, but then it tries to go back to the 0 line, and again the classically forbidden range is very close, so it cannot reach the 0 line again, etc. And the boundary condition we have in these cases are, if we are looking for a solution in which the energy is less than V of x in the limit V of r, let's say r goes to infinity, then our solution should go to 0 as r goes to infinity. Because in the classically forbidden region, it will have this exponential decay. And this is our boundary condition. And in fact, it turns out that this time-independent Schrödinger equation if you look at this equation, that equation in general has only for certain values of E or of the energy, it has a solution that goes to 0. You see, the problem is, if you look at the E less than if you look at the solutions in the classically forbidden region, well, you see, they try to approach 0, but then they can increase. But if they start increasing, that means the wave function will diverge at infinity. If the wave function diverges at infinity, it will not be normalized. So we cannot really give it a probability interpretation, etc. So if we want a normalizable wave function, that's another condition we are imposing on our wave function. They have to be normalizable, and they have to satisfy the Schrödinger equation, etc. So it has to approach the 0 line, but it should start increasing, if it ever does, only at infinity. That is a strong condition on the wave function. So only for various values of energy E, they will satisfy this. You see, if it approaches the 0, the second derivative is 0. So it should stay there after it approaches the 0. For other values of energy, it's avoiding the 0 line, but either it never touches the 0 line, so it starts increasing again, or it might touch the 0 line but cross the 0 line, and the wave function becomes negative, and so the solutions will just go to minus infinity. In both cases, it will not be normalizable. So the only acceptable solution would be the wave function should just approach the 0 line, and at infinity it should become 0 for us to have a normalizable solution. But this is only possible for certain special values of the energy E, and hence we have the energy quantization. And energy quantization is basically due to this condition over here, that our wave function should go to 0 at infinity. Now, for example, if you have, if you look at the other case, when energy is larger than the value of the potential at infinity, well, then the wave function need not go to zero anyway. And those are what we call the free solutions. They can just go up to infinity. And those states don't have a discrete energy spectrum. There's a continuum if E is larger than the potential at everywhere. Any questions?
Hocam bu klasik olan izin verilmeyen alana geçişleri deneysel olarak görülüyor mu?
Well, you see, what we know is classically, especially in condensed matter physics, we can create systems, for example, the electrons. We can create regions in which here we have the classically allowed regions. Here classically allowed. Here classically forbidden. Then we send electrons. Well, we basically send the current. Classically, those electrons should not be in the second region. This is region 1. Region 1, region 2. Classically, the electrons should not be able to reach region 2. They are blocked. But we do observe electrons in region 2. We cannot really look at the classically forbidden region, but they reach region 2. That's called tunneling. We do observe this tunneling phenomenon, which shouldn't appear classically.
Hocam harmonik osilatör denklemini klasik problemin klasik denklemler çözmüş olsaydı kinetik enerji ve potansiyel cinsinden nasıl bir denklem elde edecektik en sonunda?
I didn't understand the question.
Yani bir tane kütlemiz olsaydı o harmonik osilatörün içerisinde
Okay.
o sonuçta bir diferansiyel denklem olacaktır.
So this will be the solution of the position operator. Position as a function of time. Classically speaking. Instead of the expectation values, just put in the corresponding classical numbers.
Yok, sadece şeyi merak ediyorum da hani burada dalga fonksiyonu yorumlayışımızdan ötürü osilatörün dışında bulunabileceğini iddia ediyoruz ya.
No, it's the solutions. I mean, we are not interpreting yet what the wave function means. We will try to understand what this wave function means in the next hours. But it's just a solution. I mean, there is no reason why psi should be zero if energy is less than the potential energy. The solution of the wave function need not be zero. It's just the equation that is telling us that. And then now we will try to interpret what it means. What will be the classical limit? Well, we already have one interpretation, that is the probability of finding the particle. So basically this wave function tells me that it is possible, the probability that we observe the particle in the classically forbidden region is non-zero. So that's what it basically means. Well, the probability of observing there is kind of, I mean, how do you measure that? I mean, when you measure the particle in the forbidden region, most of the time you just destroy the system, you change the system. And most of the time it just becomes classically allowed. But what we can do, what we actually measure, is whether an electron passes through a classically forbidden region. That is something we can do. without changing the classically forbidden region. And that is experimentally verified. Most of the electronic devices are basically work because of this tunneling phenomenon. Okay, let's give a 10-minute break and we will continue after the break.